Howdy everybody. Today we are going to do an example that combines probability mass functions and conditional probability mass functions and independence and functions of random variables. I know now you can't wait to get started, right? So in section 2.4 of the textbook, that's titled Probability Mass Functions, and it's really just kind of a review, but I wanted to point out a couple of things that you need to remember. In this textbook, we use a lowercase p with a lowercase x to indicate that we have a discrete random variable. So we know that a probability mass function is specific to discrete random variables. I'm going to write that down. There we go. And you'll notice that these authors tend to put the, because we're often going to be working with more than one variable, to indicate that we're talking about random variable x, they will subscript it with an x here. I guess really what I should have done was make this a capital X because we're talking about random variable x. And again, I want to remind you that my notation is that when I'm talking about a random variable, I will put an underline under it. So here we have, and I've kind of mixed it up a little bit here just so you can get used to a couple of different styles. They all mean the same thing. If I sum up over all of my probability mass values for all x, and that really should have said all x there in the summation, we know we have to get a 1. We also know that the CDF for our random variable x, and the authors may also refer to it as with a little subscript like that, we know that that's the probability my random variable x is less than or equal to a specific value. We also have joint probability mass functions here. We have n different random variables. We have x1 is a random variable, x2 is a random variable, xn is a random variable, and then we have those very specific values there. And just as a review, we know that this function here is the probability that this random variable is equal to x1, that this random variable is equal to x2, and so on. So just a little bit of a review of notation there. And then in section 2.5 and 2.6 of the textbook, they kind of go over some review here of, I feel like I'm not square in the view here. Does that look right? I have a thing about symmetry. There we go. Okay, so here we have a joint probability mass function that is conditioned on some event A, and we would compute that probability by looking at the joint probability mass function divided by the probability that A occurs. Notice I didn't put an underscore under A because A is actually just an event. It's not a random variable in this case. Similarly, if I want to do a conditional probability, I see a typo here, a conditional probability on x, so this should not have a y in here at all. Remember, I'm updating my slides from 5 years ago, so once in a while I'm going to come across a mistake here. Apologies. So the probability mass function of x conditioned on a specific value of y is going to be that joint probability mass function divided by the probability that y equals something. And again, we might want to subscript it that way. It's possible that way. Okay, so there's a nice example in the textbook. I really like it because it helps us flex our probability muscles with respect to discrete random variables, joint probability mass functions, and conditional probability mass functions. And the example that the authors use here is something called, the example is called the minibus. And the way the minibus works here is we've got a tiny little bus that can only hold 5 passengers at a time. So reading the text up here, we can only get 5 passengers on this minibus. The bus is never going to depart empty. But it could depart with 1 person on it. It says each possible number of passengers, x, is equally likely, and passengers can be male or female. And it says given that the departing bus has exactly x passengers, so we can have up to 5, remember we can never have 0, each possible combination of male and female passengers is equally likely. So I'm going to use, I may hate myself for doing so, but I'm going to use 2 different colors maybe 3 different colors here. So let's start out with this X, and I'm going to underscore X because I'm going to make it a random variable. So I am going to denote X up here as X is, let me see if that's in view. Yep, X is the number of passengers on the bus. And then I'm going to introduce 2 other random variables that I'm going to be needing for this problem. I think I'll use, oh, it should stand out here. Green will stand out, and orange always stands out quite nicely. So I'm going to let M, capital M, is the number of males on the bus. And I'm going to let F, pretty obviously, denote the number of females. This is kind of a turquoise. I like this color here. F is the number of females on the bus. And so let's see, what could these values possibly be? We know that the number of people on the bus is never going to be 0. So we know that my specific values of X can be, we can have one person on the bus, 2, 3, 4, or 5. And another thing we should note is that X is going to be a random variable that is actually a combination of, or an addition, a summation of the number of males on the bus plus the number of females on the bus. So how many males could be on a bus? Well, that could have 0 though. We could have 1 female and no males. So we could have 0 males on the bus, or 1, or 2, or 3, or 4, or 5. And if M equals 5, that means that F must equal 0, because the sum is going to have to equal one of these values of X. So we also know that we could have 6 possible values of F. But these are going to be related to each other because they can't exceed a certain number. So the question here is asking us to determine first. It says, identify the sample space and the joint probability mass function for this experiment. So I'm going to just underline here where I have males are orange and females are this color here. Great. So let's take a look at it here. X, again, is going to be the number of people that are on the bus. And if you don't like X, or rather I should point out that this value here, this has to equal the sum of however many males we have and however many females we have on the bus. So if we have just 1 on the bus, that means we could have 0 males, 1 female, or 1 female, 0 males. And then you can identify and go through here and show that these are all accurate. So if we had, say, 4 people on the bus, then we could have a combination of 0 males, 4 females, 1 male, 3 females, and so on. So I think that you can verify this on your own if you wanted to pause the video here and verify that. So now it says, identify the sample space and joint, so that's actually what the sample space is. So let me point that out. So capital S is the sample space right here. That shows me all of the possible combinations that we could have. Now, one of the things that they tell us in this passage here, they tell us a little bit of something. They say that given that the bus contains exactly a certain number of passengers, that each possible combination of male and female is likely. So what does that mean? Let me go with the first one. It says, what does it say there? Hang on. Each possible combination of male and females is possibly likely. Oh, and then up here it says each possible number of passengers is equally likely. So what does that mean? Let me highlight that to kind of point that out. It says each possible number of passengers is equally likely. So that is referring to these values of X here. I'm not sure that, oh, that did show up, right? So what that is really saying is that we know that the probability that the number of passengers, which is a random variable, is equal to some, I'm going to use just I here, a certain value I, that is equally likely. So we have 5 possible values there, so that would be 1/5. So this is a discrete uniform distribution, and that would be for the number of passengers being 1, 2, 3, 4, or 5. So I'm highlighting that in yellow so that you understand what that piece of information in the problem is referring to, okay? Then it's saying, once we know how many passengers are on the bus, that each one of those outcomes is equally likely. So what does that mean? And I didn't bring another highlighter for that, so what we'll do is we'll just kind of circle this in a different color. Let me see if this comes out. Let me see if I can see that color. I don't like it. I'm just going to circle it in something else. I will circle it in brown. So now they're saying, given that the departing bus contains exactly X passengers, each possible combination of male and female is equally likely. So what does that mean? As an example, they're saying that 0, 1 occurs with probability 1/2, because there's only 2 here, and that 1, 0 occurs with probability 1/2, and so on. So right here, each one of these here, given that we have 2 on the bus, this is equally likely as this one as this one. So each one of these events or outcomes, however you want to call it, would be 1/3. Each one of these is 1/4, 1/5, and 1/6. So I wanted to make sure we understand what the problem statement is giving us before we actually move forward. Okay, so I have filled out this joint probability mass function, and the rows are going to indicate what the males are. So I'm going to say rows here are the values of M. So if you like, you could say M is 0, M is 1, 2, 3, 4, 5. And then the columns, those are going to be the values of F. So in this case, F is equal to 0. Well, see, that's not going to show up very good. F is equal to 1. Little f is equal to 2. I probably don't confuse this little f with like a PDF, please. I'm using f as a random variable here just because it's convenient. Okay, so there we go. Now, how do we get these values? Well, let's take a look at the zeros first, because I think that's the easiest. First of all, we know that we can't have a bus departing with no one on it. So when we have 0 males and 0 females, that probability is going to be 0, right? So this probability right here is the probability that M is equal to 0 and that F is equal to 0. And we also have a capacity of 5. So that's what all of these zeros are down here. So we can't have 2 males and 4 females on the bus, or 2 males and 5 females, and so on. So all of these zeros here correspond to the fact that my bus has a limited capacity of 5 people on the bus. So let's just pick out some of the probabilities that I've pre-computed here and see how that came about. All right, let me see. Did I do everything I wanted to do here? I think I did. Okay, good. So let's go ahead and let's take, let me see. Let me grab one here. I'll use it in blue. Let's grab M is 0, F is 1. Let's grab this one right here as an example, okay? So if we wanted to figure out P, and we'll call this MF, and we have 0, 1, we know that that is the probability that the number of males on the bus is equal to 0 and the number of females on the bus is equal to 1. And how are we going to get that? Well, we're actually going to use a conditional probability here. So we're going to get this value by saying, well, this is equal to the probability that we have 0 males and 1 female, given that we have only one person on the bus in the first place. So we know that x is equal to m plus f. So I'm just going to say, given that x is equal to 1, and now to get this conditional part out, we're going to multiply that by the probability that the number of people on the bus is equal to 1. And so that will give me the value that I want, right? And that was why I spent some time with the yellow highlight and also with the brown highlight. So what have we got here? The probability that that we have a 0, 1, given that we have one person on the bus. Well, 0, 1 occurs with a probability of 1/2, because there's only 2 outcomes when we have just one on the bus. So this piece of the equation is going to be 1/2. And then what is the probability that x is equal to 1? Well, that's the yellow highlight here. So the probability that we just have one person on the bus then is 1/5. And so that's where that 1/10 comes from right here. Just kind of wanted to point that out. So that's where that 1/10 comes from. Let's do another one, just to make sure we kind of understand this. I'll grab one more, and then I'm going to ask you outside of this lecture to verify either all or at least enough of these that you are comfortable with it. So let me grab another color here. Let's take a look at 3 and 2. So 3, 2 will be 3, 2 is 1/30. So I'm going to color this one, circle this one in a purple color. I think that will come out. I hope it does. And show you where that 1/30 comes from. So let's do that one down over here. So the probability MF of 3, 2, that's going to be the probability that we have 3 males on the bus and 2 females on the bus. I probably should have done this in orange and whatever, but I don't know, forgot to. 2, and I'm going to do the same thing here. I'm going to say this is the probability that we have 3 males and 2 females, but given that we have 5 people on the bus, so m plus f, which is x, is equal to 5, and then I have to multiply that by the probability that we have 5 people on the bus. And so now when I look for this conditional probability, I'm going to see that we have a 3 and a 2 right here. And what is that probability? Well, we said that that's equally likely. So how many outcomes have we got here? 1, 2, 3, 4, 5, 6. So this is 1/6. And then the probability that we have 5 on the bus is just from this discrete uniform distribution. And so that's where we get that 1/30 right there. So I would ask you to go ahead and do a couple more of these to convince yourself that, that this is how we'll do it. And then later on, what would be nice is if you went ahead and you double summed up here, verify this also. I'm going to ask you to verify. I would recommend finding a common denominator here instead of doing decimal places, but if you do the double sum here over all of the values of m, all of the values of f, of these probabilities, oh, why did I use an x? Good gosh. M, F, that's a lowercase p, by the way. You will get a 1. So I will ask you to verify that on your own. You can use whatever common denominator you like. I just used 600. It seemed like the easiest one for me. Okay, so let's move on to part B of this problem. Now part B says, determine the marginal probability mass function for the number of females on the bus. All right, now this is part B here. And what I did here to be able to show you how to do this is I simply reproduced the joint probability mass function from the previous slide. So this is just from slide 8. I didn't do anything new here. But again, just to remind you, and now what I think I'll do is, well, now I'll use my colors, why not? So again, this is representing number of males is 0, 1, 2, 3, 4, and 5. And the number of females, same thing. So here we have F, I should do this better here, F equals So what do they really want me to find here? What they want me to find is a PMF for the number of females, but it's considered the marginal PMF. So what is a marginal PMF? Well, this is what they want. Find the PMF for the number of females. That's it. That's what they want. And so we know that we can get that by just summing over all of the possibilities of M in combination with F. So let me take just one example here because I think this is a pretty easy part of the problem. If I were to circle, I'll make it an easy one here. If I wanted to determine PF of 3, I can get that by seeing that I have all the ways that F can be 3. So that would be, we can have F is 3 when M is 0, or remember plus is 4 when we're adding probabilities, or but or is when we add probabilities. Or we can have F could be 3 when M is 1, or we could have F is 3 when M is 2, and then we can't go any further because that means that we have 5 passengers on the bus. So if I just look at these 3 pieces here, what am I doing? I'm adding everything in the column that corresponds to F equals 3. So that's going to be 1/20th plus 1/25th plus 1/30th. And when you do that, you end up with, and I just used a common denominator, that should equal 37 over 300. You can verify that on your own. So if I want the probability that my random variable F is equal to 2, then I'm going to sum up all the probabilities in this column. If I want it for 1, sum of the probabilities in this column. And so since I showed you how to do one of the columns, I'll leave it up to you to do the rest of them as well, and this is what you should end up with. So the final summary will be as follows. If I went like this, if I said my probability mass function for the number of females is equal to, and we know that the number of females can be 0, so when I sum up this column, so I'll have F equals 0, you will end up with 87 over 300. And when you do F is 1 and sum up this column, well, it's identical to this column, so you're going to get 87 over 300 for that one as well. For 2, that will work out to be 57 over 300. For F is 3, that's the one we just did, that's 37 over 300, a lot of 7s in here. For F is 4, we get 22 out of 300. And then finally, for F is 5, we get 10 out of 300. And then again, I would tell you to verify that when I sum over F going from 0 to 5 of these probabilities here, that you will get 1. It's just a regular normal probability function here, okay? All right, by the way, you ever see me make a mistake, and I'm sure you will, in any of these slides, please let me know immediately so that I can get out an errata for the slide or for the for this video, okay? All right, we have another part here, part C. Part C says, right here, Part C wants us to determine the joint conditional probability mass function for the number of females and the number of males on the minibus, given that the bus departs at full capacity. So what do they want from me here? Well, let's take the language and make sure we understand what they're asking me for. Do I have enough room here? Yeah, I do. They want me to find, and let's work through the words here, conditional PMF. So I know I'm looking for a conditional PMF So it's going to be something, something, conditioned on something else for the number of males and females. So they just told me what my subscripts are going to be. Ah, that's a lowercase, by the way. And this will be MF, conditioned on the fact that the bus departs at full capacity. So full capacity means that my random variable x is equal to 5. So this is what they want me to determine. Now, this is not too hard to do. I'm going to go from slide 8 and work from those values as well. Is this from slide 8? Hang on one second here. 9, 8. Yeah, so have slide 8 available for reference. But here's a little remembrance here, hopefully from your conditional probability days. Whenever I want to figure this out, this is how I'm going to do it. I'm going to take the joint probability mass function of m and f, and then for each value of m and f that makes sense, so this is for, well, I'll write it down in a second, and then divide it by the probability that my bus departs with 5 people on it. And I'm going to do that for each m and f that I'm just going to say apply, because you're not necessarily going to have all of the same values. So when x is equal to 5, that means I'm only dealing with these values of m and f here, okay? So let's go ahead and apply this formula, and then we should have our answer, right? So let's start out nice and slow. Let's look for, where am I going here? Let's go here. P, M, F, M, oh, wait a minute, hang on. We'll go with the first one, 0, 5. Hang on, 0, 5, given x is equal to 5. So that means I'm going to take this value, and this is going to be from slide, as I said, from slide 8. So make sure you've got slide 8 out here. Remember, this is my sample space over here. So from slide 8, we'll have P, M, F, and then we'll take 0, 5, and then we'll divide by the probability that x is equal to 5, which we already determined is going to be 1/5. So now what we'll have is PMF 0, 5 right here. They said in the problem that each of these is equally likely. So we have 1, 2, 3, 4, 5, 6. Oh, sorry, hang on. Hang on a second. PMF 0, 5, never mind. I went off on another idea here. When we go to slide 8 over here, let me get my bearings here. 0, 5, that's going to be 1/30 over 1/5, and so that's going to be 1/6 right there. Let's do the next one here. Let's do 1/4. So P, M, F, 1/4, given x is equal to 5, and then I'll just let you fill this in. But 1/4, if you go back to slide 8, you're going to see that that is going to be 1/30 again over 1/5, and that's going to be 1/6. Well, let's just do it for all of them. We might as well. And you're going to see that they're all going to just be 1/6. So my next one is going to be 2, 3. And 2, 3, again, if you look, we're going to see we're going to be on this diagonal, right? So everything is just going to be 1/30 over 1/5 for every possible one of these. And so, well, let's just keep doing it. Might as well. It gets a little tedious, that's all. So we have 2, 3, and then we have 3, 2. And that's going to be 1/6. And then we'll have M, F, and then we have 4, 1. Also going to be 1/6. And then finally our last one will be 5, 0. And that's also going to be 1/6. And then, as you well imagine, that if we were to sum up over all of the probabilities here that we have to get a 1. It's just a probability mass function, albeit a semi-complicated one, but we will end up with 1 as well. So just to point out here, notice that the sum equals 1, which is what we expect. Okay, there's one more part to this problem. There's actually some typos on this part D, so make sure you note the typos, all right? So part D, an interesting problem, says determine the conditional marginal PMF for the number of females given that there are at least twice as many females as males on the bus. That is a lot of words here, and since I was using a particular color for females, I think I will stick with that. So what is it that they want me to find here? And let's decipher exactly what they want. They want me to find conditional marginal PMF for females, so we know that my subscript is going to be female. Conditional marginal, so we have F, but then they use the word conditional. And what are we conditioning on? That we have at least twice as many females as males. So given that the number of females on the bus is, oh shoot, I'm using the wrong color. Rats-a-rooney. Hang on. There we go. We'll just cover it up. It's fine. All is well. There we go. Given that the number of females is at least 2 times the number of males on the bus. Okay? So that's what they want us to find. Now, because it's a conditional probability, we know from past experience that we're going to have to figure out what this value is here. So jumping down here, the probability that the number of females is bigger than or equal to 2 times the number of males, how are we going to figure that out? Well, let's just go back to, this is again from right here, this is all from slide 8, just to remind you. So this is my joint probability mass function here. Let me just remind you of that. So this is actually PMF, MF. And again, remember, these are all, now I know I ran out of room over here. These are all the M's. And those are all the F's up here. So again, these are all the values of F. So what this problem is saying, given that the number of females is 2 times or more the number of males, what's our probability mass function for the females? And that's what I have delineated over here, and this is where my typos are, so ignore this for just a second. Well, let's figure out what this probability is, all right? Well, let's go up here. When we have 0 males and 1 female, does that satisfy this equation? And it certainly does. If I have 1 female and no males, then 1 is definitely bigger than or equal to 2 times 0. So this is definitely going to have, oh, why did I do X again? MF. This will be 0, 1. Definitely, that works, right? But that's not the only way that can happen. Or we could have the number of females could be 2 and the number of males could be 0. So we would have PMF 0, 2. And we can keep going, and as a matter of fact, it's going to include everything in this very first row here. So I'm just going to show all of those probabilities. 0, 3, and then 0, 4, and then 0, 5. And we're still not done. We also could have, and maybe I'll just use a different color here because it might be helpful. We could have 1 male on the bus, and that means, so for M is 1, then 2, 3, and 4 are parts of this probability as well. So now we could have MF, 1 male on the bus, 2 females. Does that work out? Yeah, that's right. 1, 2, or we could have 1 male, 3 females. That fits that, right? Or we could have 1 male, 4 females, but we can't go 1, 5, because remember 1 plus 4 can't be bigger than 5. And then there's still, let's see, is that it? I think that's it, right? We can't have 2, right, we can't. So this is it, we're done. If the number of males is 2, and then the number of females has to be at least 4, well, we can't have a 2 and a 4 on the bus because that would make 6, which is larger than 5. So now when I add up all of these probabilities, and I think I'll just write them kind of next to it. So we're going to have here, this will be 1/10 plus 1/15 plus 1/20 plus 1/25 plus 1/30. And then down on the next row, the appropriate values will be that 1, 2, that's going to be 1/20 plus 1/25, right here, 20th, 25th, and 1/30 plus 1/30. And when you get all done with all of that, you will end up with that the probability that the number of females is bigger than or equal to 2 times the number of males, add it all up, and common denominator, you can simplify it if you want to, I just didn't, 124 over 300. You could certainly simplify it if you want to, but there you have it. And I'm going to need that value in just a minute. So now, what I'm really looking for, again, are these values here. Now here's where my typos came in. We can have the number of females, the lowest value that F can possibly be when M is 0 is 1. So F has to be at least 2 times M, and we can't have them both be 0, right? So F, the number of females, could be 1. Well, it could also be, you can just look here to see it, it can also be 2, and that's where my typo came in. So F could be 2, F can be 3, F can be 4, well that was an easy correction. And let me see, is that it? Can it be 5? I don't think it can be 5. I think I might have a few too many here. Let me think. Here. Oh yes it can, it's right there, doy. Okay. There we go. Okay, now we'll just go ahead and we'll apply the formula that we know and love, and I'll just do it once and then I'll have you finish the rest of it, okay? So for me to figure out this probability here, how am I going to get that? This is going to be my joint probability mass function here, little p, m, f, for, the only way this can happen is if f is 1 and m is 0. So that will be 0, 1, and then we divide by the probability that the number of females is bigger than or equal to 2 times the number of males. And so the probability 0, 1, that is 1/10. And then we just figured this one out to be 124 over 300. And this probability then reduces to, and I'm just going to keep the denominator, I'm not going to simplify, 30 over 124. Let's do another one. This one here, for f to be 2, given that f is bigger than or equal to 2 times m, you can see that 2 occurs twice. It occurs here, and it occurs here. So now we're going to determine that the numerator now is going to have 2 probabilities in it. So f is definitely 2, and we meet this condition when m is equal to 0 or when m is equal to 1. So we have to add one more term to our numerator here. So we could have m is 1, f is 2, and then we divide again by the probability that f is bigger than or equal to 2 times m. And so when you do that one, you will have 1/15, so 2 plus, and then we have 1/20. Ugh, sorry, I got kind of cluttered here. Over 124 divided by 300. Anyway, the final value here, I got a little bit cluttered there. That ends up being, let me just check my notes here. You should get 35 over 124. And then I'm going to let you do the rest of these. I'm just going to tell you what the values actually are, all right? So following along in the same spirit here, you've got to figure out all the ways that f can be 3 under this condition. And like, for example, the next one, right? You're going to be adding up the term 0, 3. You're going to be adding up the term 1, 3. Just those two, I guess. So that will end up being 27 out of 124. And then f of 4 will work out to be 22 out of 124. And then finally, f of 5 will work out to be 10 out of 124. And if you sum f going from 1 to 5 over this here probability, well, this is what we did. I mean, this is all of that, right? You all understand that? Of little f given, I probably should have these as lowercase f's, but I'm just going to leave it that way. They probably should be lowercases now that I think about it. Sorry about that. What you're going to end up with is 1, and you will. So here endeth this particular set of slides, and have a wonderful day.